11 minutes. Hey, good morning. Lecture number 3, and it is 8:15. So I guess that we are ready to get started. I can see that we have a very few number of students this time, but I suppose that that's simply because it's a Monday morning and you guys are, I mean, you guys are here and other students are hopefully coming a bit later to this streaming. So what will happen today is this. So we can close the discussion about the three-dimensional multibody dynamics, and then we could open a completely new area. And that's completely new area is related to how to describe deformable bodies. This is a story that is a bit lengthy, and it covers all different kind of aspects in the mechanical engineering, including the vibration, structural properties, and so on and so forth, damping as well. And in total, the explanation related to flexible bodies will take 4 weeks. And of course, part of that is really related to multi-body system dynamics, whereas other part is related to more conventional finite element approach. Also a little bit about this eigenvalue analysis, which is a fundamentals in um, in description of vibrations. And then we're going to look something that is called modal reduction technique. And that's going to be more or less the main topic when considering the first midterm exam, which again will be in week 8. So we leave a three-dimensional description a little bit aside for starting from this. I mean, after I would say 15-20 minutes, and then we're going to discuss about the flexible bodies. And I think that's going to be quite a bit of fun. There's a lot of things that you're already familiar with, but hopefully my explanation is a little different that you're used to deal with. So that's what follows. And yeah, pretty much it. So without further ado, let's take a look what we discussed a week ago. So a week ago, uh, we finalized the description based on 4 parameters, rotational parameters. And we concluded that the most often used approach is, I mean, kind of like the mother of all the approaches is a Rotational equation. So it's not frequently used itself, but other formulations can be somehow put back to the Rotational equation. It kind of explains what is the deal with these 4 parameters, of the use of the 4 parameters. Well, like we discussed a week ago, and shortly a week before that, the concept of Rotational equation is based on the rotation of a vector. So you have a vector, like let's say that this pen is describing the vector. And what you're going to do then is that you will introduce assisting vector or additional vector, which is unit in a length. You put this assisting vector to the origin of your vector, like this finger here is now representing this assisting vector. Then you can introduce the rotation around this unit length vector, and the amount of rotation is theta. And once you do that, then you can use a bunch of mathematical manipulation, and you end up to have a 3 by 3 rotation matrix, which uses 4 parameters. So what are these 4 parameters then? Well, they are components of vector v, skew symmetric form of vector v is shown here. But those parameters are, of course, v1, v2, v3, because we are in a, oh, no transpose there, because we're in a 3-dimensional space, and angle theta. So a total of 4 parameters. And very important to understand that this is not trying to explain that the body can rotate in 4 different ways. No, that's against the physics. This is against our experience in the real life, but 3 ways only. So it meaning that these 4 parameters are not fully independent. So there is something that links them together. And what links them together is the fact that this vector v is unit in a length. So its length is 1. So that can be expressed mathematically such the way that the first component power 2, second component power 2, third component power 2 have to be equal to 1. So that's your constraint. So 4 variables minus one constraint, so leaves three three degrees of freedom, describing the three ways that the body can rotate. So why to torture yourself to use these four parameters? Because obviously they don't match with the common sense. They are somewhat hard to use, and there seems to be a little bit of concept that the human brains are not able to adapt. So why don't we just use three parameters, three angles, and be happy with that? Well, problem is this. So whenever using three parameters, rotational parameters, you have a singularities or other mathematical difficulties, which is going to be very, very hard to deal with. So methods based on four parameters are mathematically more fluent. So they're mathematically more pleasant, and they don't suffer from the problem similar way that the method based on three parameters. And like we concluded a week ago, these three parameters, they kind of make sense. And most of the software, they have post-processing and pre-processing based on three parameters, whereas the engine itself, whereas the solver itself is based on four parameters. And there's, of course, possibility to create the mapping between these two sets. So 3 to 4, 4 to 3. That's, of course, possible. Okay, so I mentioned that the Rotational equation is like a basis of method using that I based on four parameters, but not frequently used. So what is the one that is then frequently used? Well, that is the one that is Euler parameters. And again, there is a easy link to a Rotational equation, and the link goes such the way that you introducing this, or you using this trigonometric functions in your Rotational equation, and then you have different naming technology. You're just calling the different components in your Rotational equation by different names. And these names are theta 0, theta 1, theta 2, theta 3, as shown in this list here. So this is the name tags. And when using these name tags or substituting these name tags to this equation here, this is how the 3x3 rotation matrix look like. Now, this too is based on four parameters. So I'm using four parameters. And still I have, look at this. So I have this vector v here. So as the vector v have to be unit in a length, this is something that also introduces a constraint. So original four Euler parameters are not independent, but they are related because of the vector v. Because they are related, that's one's constraint. And what is left is a 3 degrees of freedom, if you want to put it this way. Okay, so that's what it was. And then we applied this three-dimensional kinematics to robotics, and we learned the method based on which is called 4x4 transformation matrix technique, which is a very simple for us because we know that quite a bit about the kinematics already. So what we did in this 3x3 robot kinematics representation was that we relocate our kinematic notation. So this is the kinematic notation we're using over and over again. We took this translational component and we placed that to upper right corner of 4x4 transformation matrix. And then we took this 3x3 rotation matrix and we placed that to upper left corner of this 3x3 rotation matrix. So this submatrix is this one here is 3x3, and this is a vector 3, vector that consists of three components. What is left is the last row, and the last row we simply put it in such a way that all the components are zeros except the diagonal one, which is set to be 1. This one is sometimes called as a scaling component or scaling factor. For me, it's a little hard to understand why there would be a need to do any kind of scaling, because this is more like mapping, moving from one coordinate system to another without any kind of magnifications or anything like that. Okay, so how it works then? Well, now you have these 4 by 4 transformation matrix, and now you can use this to describe the particle with respect to your reference coordinate system. Exactly what we did in multibody system dynamics. Now the difference is that the vector u bar, which was used in a multibody system dynamics, that too is called a bit differently. It's called as a vector p. Now vector p is a function of vector u bar, as a vector u bar is located in it's occupied the first three components of a vector p, and the final remaining component again is set to be 1. And that's it. That's it. Okay, so what's the point? Why? Why to do this? So is it like just good to know that there's another way to describe the kinematics? Mm, Not necessarily, because this 4 by 4 transformation matrix representation allows you to use a recursive representation. It allows you to recursively travel from one coordinate system to second, third, and fourth, and so on and so forth. And that makes it possible to create the kinematics in a very straightforward manner. So it's like a shortcut to describe kinematics, robot kinematics particularly, because robots are typical these recursive structures. So meaning that position and orientation of first body depends on the position and orientation position and orientation of second body depends on the position and orientation of first body. And then the third one is depending on second and first. So that's kind of recursive nature. So you need to know all the prior component to be able to express your current component translation and orientation. And that's the typical structure of robotics. Now, that's where this 4 by 4 matrix representation becomes to be handy. Okay, so how it works then? So it works such the way that you're creating this 4 by 4 transformation matrix representation between the different coordinate systems, representing bodies. And then you multiply them together, and that allows you to travel in this recursive chain from root to whatever you need to travel. And that's your kinematics. It takes a little while to use to deal with this, but it's actually very handy and is heavily used in robotics. And now you know that it's like cousin, brother of kinematics used in multibody system dynamics. It's different, however, in a sense that you cannot map things back, so you cannot travel back easily. Meaning that this notation that was valid in a 3 by 3 rotation matrix representation, that doesn't hold in a 4 by 4 matrix representation. But that's okay. That's the minor disadvantage. And a week ago, we learned that there's this technique called Denovitt-Hardenberg, which is exactly this 4 by 4 matrix representation. But this 4 by 4 matrix representation goes such the way that you predefine 4 parameters. You're predefining the 4 possible ways that successive rotations, successive coordinates are connected together. And these parameters are length of an arm, this one here, how much they're twisted, like if there's a twisting of the body, this one here. What is, let me see, D here, how much they're separated in a translational joint, like how much they're away from each other. That's one here. And what is a relative rotation between the bodies? This one here. When you multiply them together, this is your 4 by 4 transformation matrix representation based on Denovitt-Hardenberg. Okay, so why to do it? Well, you can do it because then once you have a robotic structure, then you can set these coordinates as shown here, and then you can build representation corresponding each of the bodies of the system. And here's an example of that. So the body number 1 is this one here. And body number one, what you do here is that you just creating or you defining what are these four parameters based on Dynamo-Hartenbreck. And then you need to make sure that you are setting the parameters in such a way that the second body will be easy to define. So that's how it goes. You have to do coordinate rotation here. Otherwise, the next body will be very, very hard to describe. Then you take your second body, you do that similar kind of concept, and you take your third, well, let me see, this is supposed to be 2, and this is supposed to be 3. And then you're just setting these parameters. And once you have this table ready, that's it. Then your kinematics is practically ready, because next thing you need to do is that you need to create a 4x4 matrix representation corresponding this body, and this body. So there's going to be 3 matrices in total. And once you multiply these matrices together, you can figure out what is the position of this end effector of the simple arm robot system. So that's how it goes. Okay, moving on. And I got the comment that is something that I cannot understand that. I think at the last week too, I got a couple of comments that it sounds that this is somebody's watching the lecture using a mobile phone, and the mobile phone is in a pocket, and there's a like pocket message. That's how it looked to me. Okay. Then back to the multibody system dynamics. And in multibody system dynamics, when we're using this kinematic notation, we used course in last semester and this course too. There's something that is a little bit of surprising. And something that is a little bit of surprising is that if this is a particle position, and when you differentiate this with respect to time, so let me take it here. So it's going to be r dot plus a dot multiplied by this u bar. And when you look in details, what is this component? Remember what we, in a in a course that was last semester, we looked at the two-dimensional space only. And we were able to conclude that this one here in two-dimensional space, and hopefully I'm not getting too confused. In two-dimensional space, we were able to write it like this. And in three-dimensional space is way more complicated than that. So that's not valid. But what it is then? Well, a dot in three-dimensional space. Okay, let me make a little bit of a more clear. Let me take this away. A dot in three-dimensional space can be put it in a writing like this. So there are two different alternatives. So it's angular velocity with respect to global coordinate system multiplied by rotation matrix. And now I need to double check, like, was it there? Yeah, it was like this. So this is how it went. Or alternatively, you can write it like rotation matrix. And this was a skew symmetric form, U bar skew symmetric form. These are the different possibilities. And now why this is like, okay, so is this just a mathematical manipulation? Well, yes and no. But there is a big story behind. Like, why is that I wanted to tell this to you? I wanted to tell this to you because, angular velocity vector we received from this differentiation here. It's very important to understand that that's not the same than time derivatives of your rotational parameters. So what are your rotational parameters? Let's get started that. Your rotational parameters are this vector theta component. And now depending what are the components you use. Let's say that you're using Euler parameters. They are theta 1, theta 0, theta 1, theta 2, theta 3. These are your tenorized coordinates. And remember, what are the tenorized coordinates? Those are the ones that defines the translation and orientation of every single body in your system. So those are the ones you wanted to solve. Definitely, those are the ones you wanted to solve. And now, when you differentiate this one here with respect to time, you will get this one here. And that's not the same than angular velocity. And that's the extra complication, serious complication in your notation, because you need to map them to be equal. How you can do the mapping? Well, you can do the mapping with help of G matrix. And G matrix is the one that have no clear physical interpretation, but it relates your angular velocity and time derivatives are your generalized rotational parameters. I know that the lengthy statement and maybe hard to understand, like, okay, but yes, how is it this is making my life different? It makes your life different because typically you wanted to describe your inertial properties using the body reference coordinate system. And then you wanted to use these rotational parameters in your computing. How you can do the linking, how you can make it possible to do that. That all will be with help of G matrix. And that, by the way, is an answer to the question that we looked a week ago, and the question that may appear in written exam, model exam, next midterm exam. Okay, I know that this is a little bit painful and it is Monday morning and all that. So let's just leave this up with a little less attention right now. We will get back to this when we're summarizing all the material for midterm exam. All right. So this was my this was my description of velocity, and look what happened here. So originally I described my particle velocity as it is shown here. I can do this also with help of vector, excuse me, the matrix R, like can be made it like this. Okay, but here I don't have directly my generalized rotational parameters. So I have translational parameters here, but the rotational parameters are missing. And now we'll take this into play with help of the G matrix. And once I have a G matrix, this is how my velocity look like. And this is this. This G matrix is from this on, is in every single notation we're going to use. So it's over and over again with us, like it or not. Well, of course, we are not going to like it because it's so complicated, but it's always with us. All right. And now what follows is I'm shortly going to show the acceleration. And then I'm shortly going to show how is equation of motion. But the main concept, the main message that I wanted to deliver is this one here. Angular velocity, generalized angular velocities can be mapped together by using a vector G. That's what I would like to express here. Okay, so here, this is how the acceleration of a particle look like. So the terms are exactly the same that in the case of a planar case, but when I look at this in details, when I look at this in the case of G matrix, this is something that we are kind of familiar with. But when I put it in a form that I can do the computing, because here it's so hard to do the computing because roughly speaking, the story goes like this. So you can go from angular acceleration, you can go the angular velocities. But from angular velocity, you cannot come to T with ease. So you have to travel this way by G. That's where it comes from. And otherwise, it's not going to just work out. Okay, so what happens if I express my acceleration using the G? Well, now you know already how it's ended up to be. So it's going to be big mess, huge mess. Because now this time here, this acceleration is expressed in terms of generalized coordinates. This one wasn't. Why not? Well, look at this. It was alpha and omega, but not this guy, not vector of rotational parameters. That was missing there. So that's why. Okay, so here is our acceleration. And now hold on. I'm going to simply substitute this to my virtual work of inertial forces, and I'm going to end up to have mass matrix and quadratic velocity vector. And yes, there's going to be a big mess. They're going to look very bad. That's okay. That's okay, because what you need to know is this concept, that which I'm going to rephrase your mind before we end up to be in a midterm exam. Okay, remember how it went. So it went such the way that we first look at how is the inertia forces, and inertia forces are mass multiplied by acceleration. And mass, when we're saying mass, we wanted to take the mass of each one of the particles into account. And it goes such the way that we're taking the density of the particles into account, and we integrate the density over the volume of the body. That's how we can express the inertia forces. And now when we look at the virtual work done by inertia forces, this force here is multiplied by delta R. Delta R that allows us to map description from global coordinates to generalized coordinates. And now that this is like how can I put it in a way that makes you feel good? Because I know you guys are miserable. Like what? Why is that I'm never gonna get rid of this virtual work and this mapping, this and that, and the reason is that I would like you to understand this concept, and you may wonder like how much this make a difference in terms of design of machine and real-time simulation and so forth and so on. Well, this is something that as a master level student is important to understand the theory behind. And why is that? Because then once you have a good understanding about the theory behind, then you can be 100% sure that you're not going to misuse the technique that you're about to learn. Okay, I don't know if this convinced you or not. But anyways, we will have let me take a look. Couple more slides. Super painful, most painful slides of this course for sure. All right, so mapping, what I mentioned just less than a minute ago, mapping between the global coordinates, generalized coordinates can be expressed using this equation as it is shown here. And once I substitute that to my virtual work of inertial forces, it just started to look very bad. And this is how it looked. This is actually exactly the same how it was in a planar case. But you understand what follows next. It's the substitution to this component. And remember how bad it was. It was pretty bad. And now when doing that, this is how it looked. So this was my acceleration expressed using generalized coordinates. This is my mapping. And once you do the substitution, this is how the virtual work done by inertia forces look like. And it looks very sad. It looks very sad. But let's see if there's any sense that anything we can learn from that. And I think there's quite a bit we can learn from that. Okay, first of all, let's just do the mathematics without no further thinking whatsoever. And the component that you soon will find here is mass matrix here. And quadratic velocity vector, exactly like we did this in a planar case. Difference is this. This time, the mass matrix, in particular the quadratic velocity vector, are way more complicated. But that's okay. That's okay. But something that I would like you to learn is that, look at what is here in the middle. This is obviously inertia tensor. Inertia tensor that is 3 by 3. And it's 3 by 3 in a way that diagonal components are mass moment of inertia. Off diagonal components are mass product of inertia. Why this is important? This is important because this is then mapped to any representation of rotational parameters you want. How? With help of G. So that's what it is doing. The G is your friend eventually because it is doing the conversion from your symbol inertial representation to any computational parameters you decided to use. So now it started to make some sense. And this, by the way, was something that I really wanted you to learn. So if you understand that, I don't want you to know to any more than that. That's enough for sure. And then the quadratic velocity vector is just a big mess, which we can leave with a less attention. But the mass matrix, like I mentioned, the mass matrix looks like this. So this is 3 by 3 part of the mass matrix, and then this one here is my inertia tensor. And inertia tensor is then multiplied by vector t here. And this inertia tensor, when you look at the details of the inertia tensor, is exactly like I said. So mass moment of inertia is located in the diagonal components. Mass product of inertia is located in off-diagonal components. And this is kind of beautiful because then you can use your conventional inertia tensor and then map to this any numerical representation you want. And that's the story in total. And these are just showing the details of the computation. I don't think you wanted to do the computation by yourself. And the reason is that using this kind of volume integrals, that's not very practical. But instead, you want to use some pre-calculated tables. And if you don't have a pre-calculated tables in your use, or your geometry is so complicated that you cannot do it that using pre-calculated tables, then you wanted to use CAD software of some kind that doing this computation for you. And then you just do the mapping to whatever parameters you decided to use. That's it. That's how it goes. And this is where I would kind of like to stop. But 3 more slides for your information. This is just for your information. I don't expect you to learn that much from these slides that are about to come. Now, equation of motion in 3-dimensional space. That's exactly how it goes also in a 2-dimensional space. There is no difference whatsoever. So you can take the virtual work done by external applied forces, virtual work done by, this by the way should be inertial forces. External applied forces, this is supposed to be inertial forces. External applied forces, you put them to be equal, or you subtract them from each other, and the result's supposed to be 0. And this is how you can express your equation of motion. This one here, how they are placed here, is not necessarily equal to 0, but you can force this to be 0, like we did in a planar case. And you can do this forcing by using 2 different techniques, which are embedded technique and augmented formulation. So that's substitution or adding the constraint. So those are the 2 different ways. Now, embedded is a substitution. So using coordinate partitioning, you substitute your constraint, this equation of motion, and then you can ensure that this virtual displacement is kinematically admissible. And when this is kinematically admissible, then you can set this equation to be equal to 0. Or you can add your constraint to this equation with help of Lagrange multipliers. So those are the 2 different ways. When using these Lagrange multipliers, you can get one extra component, which is a Jacobian matrix. That's constraint, differentiated once with respect to your tenorized coordinates, multiplied by Lagrange multipliers, and then you can get this differential equation. But this differential equation needs some additional information, and that is that your constraint have to be equal to 0. So you have this differential algebraic equation, which you can convert to be ordinary differential equation. Now, I'm going really fast here because if you want to learn the details, why don't you go and take a look at the notes from the previous class. And yeah, that's it. Now, I would like to close the 3-dimensional multibody system dynamics, and I'm still keep on getting these weird chat comments. That's definitely a language that I'm unable to understand. Or is it like my language settings are somehow weird in my chat window? Anyway, so we're going to close this and we're going to get started from something way more pleasant. And something way more pleasant is this. Hold on, here. Introduction to flexible multibody dynamics. And now soon I'm going to set the 2 in-class quizzes. So they are related to kind of like a basic concept of how to describe deformable bodies. And yeah, that's how we're going to get started. Now, first thing first, what are the possible questions in this subject matter, which is Introduction to Flexible Multibody Dynamics. And these are the possible questions. First one is the why a body deformation needs to be accounted in the multibody applications. Why? Why I would like to describe a deformation of a single body. So is this something that you always need to do, or you just can do it if you feel to do so, or what is the reason behind? And then a question about the basic concept, which is related to small and large deformation. And that basic concept is, or the question goes like, how the linear strain displacement relationship affect the deformation of a cantilever beam. And I think you know the answer already, but we're gonna take a look at this again and explain the concept of lamp mass approach. There's gonna be one additional question, which, numbers are not gonna match from this on. But the one additional question is like, what is numerically step system? What is, let me see, numerically stiff system? Okay, numerically stiff. What is that? So that's going to be question number 16. And those are the questions that I'm limiting myself. So I cannot ask any other question than those 4 ones from the introduction part. And then I think what happens today is that this introduction itself is so much short. And I feel positive that we have a time to look at the finite Attainment method a bit later today. And there's another set of questions, many different kind of questions. So that's 4 questions are related to this part of the lecture series only. Okay, so here are the questions again. And the 16th, which is a little hard you made to read it, is what is numerically stiff system? Okay, flexible bodies. So these are the things that I would like to get, or I would like to cover in this part of the course. And so I would like to get started from the lamp mass approach, which you guys already know. And you have a little bit of an idea about how is a floating favor reference formulation as well. But I would like to introduce the subject matter to you. And when I'm introducing this lamp mass approach, then it also becomes to be clear what is numerically stiff system. And then we're going to move on to more detailed explanation about how is a description of deformation, how we can actually describe the deformation, what are the ways to do it. And then we're going to take a look at a finite Attainment modeling. And that's about it. That's how it goes. And with that, let's get started. Let me see if we have any comments other than those 2 ones that I'm unable to read. No other comments. Okay. Okay. All right. I think this is something that I explained to you in last semester, but let me re-explain this to you. So flexible bodies. Every single body is a flexible body. Like we've been describing earlier, that we can use this assumption of rigid bodies. Well, there's no such thing like rigid bodies in real life. Every single body is a deformable. But the big question is that when the deformation is significantly enough that it affects the dynamic performance, that's something that is a big question. And of course, you wanted to model deformable bodies in order to increase the accuracy of your models. So you may get the unrealistic behavior if you're not accounting the deformation of your bodies into account. And the simple example is a boom crane, the crane, hydraulic deterring crane, the one you're using in your simulation assignment. If this arm here, sorry that this is a little bit unclear description, but if there is an arm and a mass hanging in the top of the arm, if this arm is flexible enough, then the response when you make an assumption of rigid bodies will be unrealistic. So they don't match with the reality. And if that's the case, then your accuracy of the models or the results you're able to achieve are not acceptable level. That's where you need to come back to your model and you need to look at how is it you can describe body deformation. Okay, but now the big question is, you know, if description of flexible bodies improves accuracy of your models, how you know when you need to take this deformation into account and when you can make an assumption of rigid bodies. And this is the very, very difficult question where there's no answer. There's no answer to that. There's no clear rule to make this decision when a body should be described as a deformable body or flexible body. Every now and then you can see from the scientific literature something like a rule of thumb that you should do so if you deal with a structure where the natural frequency is under this, certain or having certain relation with the frequency of your forces. But you can always find an exception when this is no longer the case. Or this mentioned that when you have a slender structure, which is unclear statement, what it means to have a slender structure, when it is slender enough that it is important. So actually, then there's there's a very large forces that apply to system. Then you need to take a deformation into account. There's actually no rule at all. So, and that's what makes your life a bit difficult. But on the other hand, it gives you quite a bit of freedom. Only real kind of way to figure it out is to use your engineering sense. Engineering sense. So meaning that you need to figure out by yourself whether or not the deformation is significant enough that it actually affects the result. But no general rule to make this decision. Okay. And now let me move on to my first in-class quiz of today. And it's this: when a body deformation needs to be accounted in the multibodies applications. And options are when large forces are applied to system, when a natural frequency of the body is low, when a slender structure is in consideration. There is no general rule to make this decision. And the game is on. And I see I already have 5 answers in my circuit, which is a bit surprising because I guess that some of you make a little bit of head start, I think. Okay, how is the success rate today? Is it 100 or less than 100? More than 100? So let me see your guesses. By the way, why is that again? Today the chat is very quiet. I remember in the first lecture, or should I take a look at the chat using my phone? There's my phone. Let me see what will be the best way to see my streaming. This, I think. Oh yeah. It's okay. So I can see that you guys are making your guesses. So good. All right. So the numbers are 100, 190, 87, 100. Oh, so I never bet on 100. Yeah, that's a wise thing to do because it's never 100. So that's for some reason never seems to take a place. 83. Okay, so I can see that we have 15 viewers. So we'll see how it is. Okay, and with that, I'm gonna close our. Hold on. The Socrative is not visible. Not this one. Sorry, I need to make a minor changes to my settings. I was not using the right kind of. This is such a small window that is super hard to read it. live. Look at this one. Yeah, that one. Okay. So here is our Socrates. Need to make a minor tuning. Okay. And we got 17 answers, which is more than we have viewers, and I think we then good to go. And the success rate today is, look at this. It's always this close to score 100. It's this close to score 100, but it's not 100. You know, there's a clear difference between the 94 and 100. And now there is a two, I think a two individuals are guessing that when the natural frequency of the body is low. Yep, there's no general rule to make this decision. So sometimes, yes, maybe the natural frequency is the case, but it's not always the case. There's no general rule to make this decision. So you can make it based on your engineering sense. Okay, now let's move on to further in our description of flexible bodies. Remember there was this question ID 14, and it's related to this slide here. Now, flexible multibody dynamics is our own discipline within the multibody system dynamics. And this own discipline, so it's like own community within the multibody system dynamics. And I'm also a very active member of that community. This community is, generally speaking, this is very scientific community. This community can be, roughly speaking, divided to two subcategories. So first one was a multibody, then subcategory flexible multibody dynamics, and flexible multibody dynamics then can be separated to two different fields. The one that is making studies by assuming that the deformation is small. And then another category, which of course you get it already. So that's another category which assumes that the deformation is large. How you know what is what? And typically description is based on how is your relation between the strain and displacement. What is a displacement then? Let's get started from that. Well, displacement, you can, if cut the corners, you can say that that's a description of deformation. How large is a deformation? So it's based on the measure between the reference configuration, which typically is your undeformed configuration and deformed configuration. And you can describe that based on each single particles in your system. Let me make a bit bigger drawing here. So if you have reference configuration of your cantilever beam like shown here, these dots here are representing the particles, and there are more particles than the one that are shown here. And then if the deformation look like this, now displacement here is measuring how are each of the particles, how is they displacement, how is the vector that describe the deformation. And you see that there's a lot of particles and corresponding deformations, but that's what it is. So this one here is a displacement. Okay. What is a strain then? This is then the material property. Now let me take this away. Okay, so I'm sure you guys have seen this picture, which is a strain stress curves. And strain is like how much material itself is experiencing the deformation. And there's a link from this U, which was this measure of the deformation, and this guy. And this is exactly what I'm referring here. How much material itself is experiencing the strain because of the deformation. That's what it is. Now this curve that I'm about to draw is this, how is a relation between stress and strain. And most of the cases we're dealing with the steel materials, and the steel materials, there's a long range when the material is behaving linearly, meaning that if the strain is increasing, the stresses are increasing in linear manner, and then there's a certain point which if you take a strains more than that, then there is a plastic deformation. And usually that's when the curve is no longer linear, but non-linear. And if you travel here, you go to this point, you check your load way, you go exactly where you started. So it's like linear deformation. Like I take this spoon, I'm introducing a little bit of deformation, but not too much. So it comes to back to its original configuration. But if I use my muscles and I twist this spoon seriously, I will close this plastic region. And when I go this plastic region, I'm no longer coming back to its original configuration, but deformed configuration. Now, relation that defines how large is the flexibility is this displacement strain relation. And how that is making a difference in our life. Well, the easiest way to look at that is that, when you introduce a point force, a cantilever structure like it is shown here. Now, if you're loading this free end of the cantilever beam, this is how it looked like. So when you look at how is the displacement of the free end here in deformed configuration, and if you're having this assumption about the linear strain displacement relationship, then you see no deformation in this longitudinal direction, in this direction which we can call X here. So there is no deformation at all. And that's okay, because you look at the picture here, that looks fairly realistic. So this is what you can see in a real life. Let me make this bit bigger. So if you have a deformation like this, so the deformation is such the way that the free end remains in a loading line, right? But if the deformation is very large, then eventually the deformation look like this. You don't see this in a real life. You definitely don't see this in a real life. But you cannot capture this if you make an assumption that your strain displacement relationship is linear. If this relationship is nonlinear, then there's a little bit of deformation in longitudinal direction, in this X direction. And that's more realistic. So that's the difference between the small deformation and large deformation. So where you need large deformation. Same kind of question like when you need to take a body deformation into account. So there's no general rule. It increases the accuracy with an expensive of computational efficiency. So that's how it roughly speaking goes. You could always kind of use it, but you don't want to use it because if there's no need to do so, then your computation are going to be very slow for the reason that I'm going to explain you momentarily. And it is related to this numerical stiffness. Okay, so here's a animation. So these are the two cantilever structures. This one here, strain displacement, the one that is closer to you, strain displacement relationship is nonlinear because you can see that the end of the cantilever beam is following the circular path. Here, this is linear because this is just a line that this free end is following. So if there would be no pendulums in the end of the cantilever beam, it would be hard to see any differences whatsoever. But the pendulums make it clear to recognize that yes, there is a clear difference. There's a clear difference. All right, then something that you guys are already familiar with. And something that you're already familiar with is this lamp mass approach, which is a kind of coarse way to describe the flexibility, but not as coarse as the something that is that was used in a very early phase of when the flexible bodies were described. And that method was called linear theory of elastodynamics. And it was simple, the method that you first computed your structure by assuming everything to be rigid, and then kind of using post-processing procedure, you afterwards estimate how much is a deformation. This was the very early way to describe the flexibility. And what came after that was this lamp mass approach. And lamp mass approach, and again, linear theory of elastodynamics, which title sounds really sophisticated. It wasn't too sophisticated method itself. It was an idea that, if you have, let's say, a pendulum like this, you first compute the pendulum behavior by assuming it's to be rigid. Then afterwards, you were estimating each one of the time step how much was a deformation. And then you were superimposing information concerning the flexibility and rigid body motion, and that was your final response. Problem was the flexibility was detached from the overall motion. And this is not what you can see in a real life. That's leading to poor responses. Okay, and now I see that there is a comment in the chat window. Yeah, so I think the question is related to the in-class quiz, and it goes such the way that so it does not depend on beam dimension. I mean about the thickness to length ratio. Thickness to length ratio, the slenderness, of course, if you have a slender structure, then it is more likely that the deformation is important to you. I guess that this is related to when you need to describe the body deformation. But there are cases that you have very thick structures and you still need to describe the flexibility. And also this one here, if it is related to this cantilever structure, in a cantilever structure, the only thing that makes a difference, I need to see where's my pointer traveling. This one here, this thickness to length ratio. If you look at this behavior, only thing you can see the difference here is that something that is called transverse shear deformation started to make some contribution. But in a bigger picture, you don't see the difference that much. It basically related to how is your cross section versus to your midline of your structure. And we will get back to that. That's shortly stated, not changing the big picture here. It can be considered as a minor detail, but not that minor because there are elements that are capable to describe this shear deformation and elements that are unable to describe the shear deformation. But again, as promised, we'll get back to that. Now, landmass approach. Landmass approach is something that I shortly explained to you. So this is a method you take your original typically beam-like structure. You divided this beam-like structure to a number of rigid bodies. And then you're introducing spring elements between the rigid bodies. And then you can describe deformation in such the way that you kind of recursively describe the deformation between your neighboring bodies. And that's how you end up to have a description of flexibility. It was used to describe all kind of structures. Here's a simulation that is like 25 years, 20, 30 years old. And this is a simulation where each of these structures were described as a flexible bodies using this landmass approach. Quality is so low that you don't really see the much of a deformation. But yes, there was a deformable bodies based on landmass approach. It's still used in certain extreme cases like wire ropes. Let's say the wire ropes, they too have a little bit of better description than the one that we currently, let me just make this a bit bigger. The wire rope you can see here, there it is. There's a hook that is connected to this crane by using a wire rope. Wire ropes were modeled by using this landmass approach. Possible to do so. You can still use it in certain cases, but now if using this super conventional way, it becomes to be computationally ineffective, computationally heavy. You see how it goes here. So you're lifting, you take your hook in different places, and then you're lifting devices. This is a box, I think. You see doubt string effect? Yep. Remember that's the fact that this transverse vibration is function of how much is the tension of the wire rope. So if it is high tension, the frequency is with a higher frequency, whereas if there's no tension, then this transverse vibration is different there. This is a little bit of different view. And again, method used to describe some kind of special components like wire ropes. Okay. A little bit of lengthy video, but maybe we can play this. We still have an half an hour time, and we can, as next we're going to move on to finite element modeling. So think we have a time to do so. Very slow video. More action, I would say, would be nice. Okay. So here are the advantages and disadvantages. The first serious disadvantage is that it's computationally expensive because it can lead to stiff system, which we get back to this later in the course, but the stiff system is something that you can kind of alleviate. You can improve the computational efficiency by using time integration schemes that are tailor-made for stiff systems. Anyways, even though that there are these integrators that are designed for stiff systems, you would like to avoid the stiff systems as much as you can, because regardless of the method you use, it's always going to be slow. What is this numerically stiff system? And my next in-class quiz is exactly asking this, like, what is numerically stiff system? So put some attention to me. Okay, so let me get started by explaining this numerically stiff system in a way that, let's take a look at this. A cantilever structure, which is modeled by using this landmass approach, like this. All right. Sorry that is a little bit unclear picture, but then you have a force that is imposed to, let's say like this. Force that for sure will introduce bending and for sure will introduce some axial deformation. And now if you have a structure that is very thick, or even if it is not that thick, it's pretty clear that the bending deformation is associated with the low stiffness, whereas the axial deformation is associated with the high stiffness. How you can see that? So when you look at the final responses of the structure, they would be something like this. This is a time, and then this is a response. So response would be like, randomly something like this. So this is how they look. But if you take a small portion of the result, and if you make a high magnitude of the result like this, you see that there is like this kind of behavior, which is hard to see in a big picture. But when you take a close look, what's going on in this structure, you can see this high frequency vibration, which is associated to high stiffness. And the high stiffness was again because of the axial deformation. Now, time integration scheme can see this. So they can recognize, hey, wait a minute, there's some kind of small vibration that takes place. So let me take a look at that. And it's tuning its parameters in a way that it is computing this such the way that each of these waves are accurately described. But do we really need it? Well, depending, of course, what you want to do. But big picture is something that you can only see when you're magnifying your results. When you look at the big picture, you don't see it. And they slow down your computation. That's, generally speaking, when I'm cutting the corners a little bit, that's what is numerically stiff. So numerically stiff system is a system. Let me take these away. It's a system where if you make a line of natural frequencies, this is hertz, there's a low natural frequencies and very high natural frequencies. And these two sets are very much separated from each other. This is going to be numerically stiff. So it's going to be difficult to handle. And this is going to slow down your computing. And when you're using landmass approach, for sure you're going to suffer from these numerically stiff systems. Another disadvantage is that it's mainly for a beam-like structure. Material damping is not too realistic, but it's easy to implement, easy to use, simple theory. So those are the advantages. And now, let me move on. Like promised, the next in-class quiz is asking, what is a numerically stiff system? Here it goes. Numerically stiff system means, hold on. Options are that the system contains low and high frequencies, that the system contains high frequencies, that all bodies are assumed to be rigid, that some of the bodies are assumed to be flexible. So what are you saying? Let me see. I still got 0 answers. Yeah, that's because I just a couple seconds back put it on. And then we're going to move on to floating frame reference formulation and finite element modeling. Finite element modeling, shortly speaking, is how to describe this deformation. What we described earlier. That's what it is. How it goes, you're going to find it out that later today. Hopefully it's going to be later today. It's already 9:21. So we have like 24 minutes to go. Okay, and the game is on. 90, 94, maybe 100. I'm kind of scared because, we're scoring so close to 100%. So statistically, it have to happen. One day it will come. And then we need to set the rules, like what if it comes? What are the things that I need to do? So is it gonna be this dancing, singing, what it is? By the way, we also need to set the challenge. I got the complaints that the last time the challenge, which was a chin-up challenge, was not so good. So you guys, at least some of you, would like to change the challenge to be deadlifting challenge, which sounds like a good plan to me. So let me think about that. What? I got some kind of message that this audio streaming is not healthy at the moment. Let me see. Let me check the YouTube. It looks okay. Okay, we got the 15 answers. Okay, so it's still a complaint that the audio streaming is not healthy. Okay, then there's a question. Okay, so then there is a a little bit something that it says that yeah. So this 100% is not going to happen. But for sure it's not me. So there's no way that I can mess this. So it's always about you guys. So it's always about you. So I keep my hands visible all the time. So I make no tricks here. Okay, so where is my Socrates? My OBS. So here's my OBS. So results of today's second in class quiz is this. Last quizzes are in a play. The success rate is okay. So it's a bit disappointment. Success rate is at 87. We got 85. 85 is very close, very, very close. So that's the winner of today's in-class quiz. And we got more incorrect answers. So hold on. Do not make any guesses anymore. So, okay, then there's a comment. no, it's not Suraj either. So I did not hire Suraj to to make your life miserable. So it's not me. It's all about you guys. Trust me. No tricks here from this end. Okay. Now, system can be considered as mathematically rigid if there is a low and high frequencies. So if there's a high frequencies, that's okay because you can tune, you can scale your integrators to deal with that. That's not a big problem. And if you have all bodies to be rigid, that's okay too. So it's not numerically stiff system yet. Okay, with that, we're gonna move on to floating frame reference formulation. Introduction first, and then what happens next is that we're gonna move on to finite element modeling. 20 minutes, so I think we do have a time to look at the finite element modeling. Now, floating frame reference formulation is conceptually very different than lump mass approach. This is the method that is heavily used, and I would say that there's no commercial software without the ability to model bodies as a using the floating frame reference formulation. Okay, so then there's a question. This is we go back to this stiff system. Can system with friction, traditional deformation, can be considered as an infinitely stiff system? Yeah, the friction is a little bit of problematic too. So friction is something that can lead to situation where there's a very high, let's say that there's a like kind of high frequency vibration. And shortly stated, you're always having the difficulties when you have this high frequency and low frequency vibration. Friction, depending on where you describe the friction, can be a source of this kind of problem. Particularly if you use a like Lucre friction or something that there's this stick slip friction behavior as a part of the model. So that's a good comment. But I was about to explain this floating frame reference formulation. So let me continue with that. Floating frame reference formulation, very heavily used. What I would like you to learn in this method is a basic concept where it is based on. And also another challenge, I would like you to understand where this name floating frame is coming from. What it is called floating frame. Because it's not so easy. As shortly stated, it's related to fact that this is finite element based. That's the way that finite element models, there's always this model reduction, whatever you use this in the real life. Model reduction, that's where the floating is coming from. And as the title implies, it means that yes, there's a reference coordinate system that floats with the body. So it's not rigidly attached, so it's not detached either, but something between. How come, like, how is it possible to have something like that? We get back to that after a week, roughly a week. Okay, so this floating frame reference formulation, you can apply that to any shape of bodies you want, because it's based on the concept, it's similar kind of concept that we used in multibody system dynamics. Remember in the original multibody system dynamics, we have this vector U bar, which we assume to be constant with respect to time. Now, what we're going to do in the floating frame reference formulation, so we're adding another component to this vector U bar. And that's the one that is describing the deformation. And that's what it is. So this is shortly stated a floating frame reference formulation. So no longer having the vector U bar as a constant vector, but another vector U bar component that is a function of time. And this describes how every single particle within your bodies are deforming as a function of time. Now, every single particle, yes, that's how it goes. So we have estimation about every single particle. But we have to do some kind of discretization. There's no way that we can describe every single particle in a way that they can have relative motion with respect to each other. That's not going to be possible because remember, there's a millions and millions and millions of particles in each of the bodies. And we simply do not have a computational power to take all the particles into account. So what we will do, end of the day, is that we will take each of the particles into account, but we limit the way that they can deform with respect to each other. And that's what is called discretization. So we are saying that they cannot, let's say the neighboring particles like this, they cannot go however they want. But there is a certain number of ways that they can deform with respect to each other. That's how it goes. But anyways, back to this kinematics. So the kinematics is this. So no major changes. So we still have this translation of the reference coordinate system, rotation of the reference coordinate system. Then we have this particle, which shows where it is located in undeformed configuration, and how is the deformation of the particle. Now this sounds like, okay, just one additional component, so not a big deal. So we can easily handle this, so not a big problem. But yes, it is a problem. This is a big problem because, then once we're introducing this one addition to this equation, this addition is a serious addition. And why is that? That's simply due to the fact that, when we started to compute the velocity, it went like this. Let's just call this guy as a vector u bar like this. It went like this, vector u bar. And then we say that, the next component, which was like this, that was 0. That was 0. But you understand that now if there's a description of deformation, this is no longer 0. And this is, you see that this becomes to be extremely involving to take this u bar into account such that it can change its numbers as a function of time. So it becomes to be very complicated. Well, not very complicated, but change the game. The one addition to kinematics, change the game, for sure. All right, so how is that we're describing this u bar f? We're going to describe the vector u bar f using, I got the voice to my headset that I was disconnected. But I guess that I'm connected. Yeah, I can see from my OBS that I'm connected again. So how is it we describe this vector u bar f with help of finite element method? So that's how it goes. So we're gonna create the finite element model, which is shown here. We combine that to multibody system dynamics. That's your floating frame reference formulation. And that's why the next thing we're gonna do is that we're gonna take a look at the finite element modeling. But prior to that, a few examples. So these are based on the code that was developed in LUT University. This is a 3-dimensional crankshaft system, and the connection rod here is flexible here. Just an example, you can simulate something like that. These are very early code, so you can see that based on the quality of visualization. The visualization is not so great. And here are some tests that are related to telescope structure. There is 2 arms, both of them are deformable, and you see that the deformation heavily depends how far off is this inner body respected to our outer body. And you can see that here, if you take a look at this animation, you can clearly see that the deformation is visible, and it for sure affects the performance. So for sure, if you want to make accurate models, you need to take this deformation into account. Okay. Any other comments? I guess not. So you guys ready to move on to finite element modeling? That's a description of deformation. So we're going to take a look at the finite element modeling. Those of you that are not at all familiar with the finite element modeling, so finite element approach, this is a big picture, not necessarily related to structural strength or structural analysis, but finite element in general is a solver of differential equations using approximate elements. So the elements that are giving your estimate about how is a final solution. And this goes such the way that you keep on increasing these elements that are like piece of solutions. You get better and better solution. But this is conceptually very different than multibody system dynamics, because in multibody system dynamics, if you have a beam-like body, that's your body. There's no need to do any kind of discretization. So it's something that you can describe by using, well, in a planar case, using 3 coordinates. That's it. But now if this would be a finite element structure, its deformation or flexible behavior can be estimated by using piece of elements, piece of structures that are dividing the structure to smaller pieces. More pieces you have, better solution you get. That's the nature of the finite element modeling. And what we're going to take a look here is that we're going to take a look at the single element to understand how is that they describing this piece of solution in a structural strength or a structural analysis. And then we can understand, how is it they can model the entire structure. But the finite element method is the one that I'm sure you have seen in real life. Those finite element models are the kind of the ones that look that there is a structure where there's a fishing net top of the structure. And this fishing net is the description of elements. And now we have many different kinds of elements. We can have beam-like elements that are designed to describe beam-like structures. We can have plate elements, more like describing the plates, cell elements, solid elements. So there's a number of varieties, what kind of elements we can play with or we can use. We can basically use almost any kind of elements we want, because end of the day, what we want from our model is this description of deformation. Most of the elements are capable to do so. So we are not limiting ourselves to beam-like structures or cell-like structures or solid-like structures, but anything you want. Pretty much everything goes. Now, elements are connected together in a points that are having particular name, and these points are called as a nodes. Nodes. And these nodes has a certain degrees of freedom, which we will take a look at in a minute. And now basically what you do is that you're combining these elements together using this node, and the nodes are sharing the elements, and that's how you can model your structures, and that's how it goes in a big picture. Here are the questions. Look how we're going to take a look at the finite element modeling. So it's going to be very different. I think this is going to be very different that you used to deal with. So I'm asking, explain how polynomials can be used in the approximation of displacement in finite elements. Explain also how safe functions can be derived from polynomial approximation. So we're going to take a look at from polynomials. Why? Well, all that will becomes clear very soon to you. What is a role of Pascal's triangle in the finite element method? That is related to, I can already tell that it's related to these polynomials, how you can describe the polynomial components that is typically based on Pascal's triangle. What is a convergency, or what the convergency rate means in finite element method. That's shortly stated already. I can tell you that it means how little or how much elements you need to use to get the acceptable solution. Because like I said, the solution gets better and better and better more elements you use. But maybe you want to use as little elements as possible. And now if there's, convergency rate is good, you can get the acceptable solution with the somewhat moderate number of elements. So that's what the convergency rate means. And there's certain rules related to convergency rate that are, again, taking us back to the polynomials. So that's where those are the three questions related to very basics of finite element modeling. Now, the first thing that is extremely important to understand before we're moving on is, let me take these away, is this. Now, here is a, let's say that here is a beam-like structure, which we are modeling using a beam element. Let's say there is a one single element, like shown here. So this is a node, and this is a node, and here's a node as well. So this node is something where element number 1 and element number 2 are connected together. Finite element modeling is all about how to describe particles between the nodes. It's all about that. And every now and then you can hear these stories that, yeah, actually it's not that, but it's finite element modeling is something that there's like spring elements between the nodes. And this behavior between the nodes can be described by springs. No, that's not the finite element method. It's not about that. It's about how we are assuming particles to behave between the nodes. That's what the finite attainment method is about. So we get started by making an assumption how the particles are between these nodal locations. And we describe them by using correct polynomials. So we're going to describe this life between these nodal locations by using polynomials. And I check that okay. Oh, now I was, by the way, I was reading this comment again about the friction, about the sine function. So sine function, I think at this, when I was reading this question about the friction again, I think that I now realized, I think that the question was related to, let me take myself back to this because I think that was related to like situation like this. So you have friction force, and this is a velocity here. And the friction is behaving such the way that there's a discontinuity in this point here. So the friction is behaving like the way that this friction curve is capable to describe the stick-slip phenomena, as the curve here is having the negative slope. And here, when there's a jump, these jumps are poison to the computing and to simulation in general. So you want to avoid the discontinuities as much as possible because the jump is going to be very, very hard to deal with. For sure, this kind of jumps can be considered to be also the source of numerically stiff problem as well, because then this is like infinitely high frequency related to this jump, and this infinitely high frequency make the integrators to be confused, and they will be having a really hard time to deal with that. I'm sorry that I'm jumping from one topic to another like that, but I was, for some reason I missed a part of the comment earlier, so now I saw that there was this sine function involved as well. Okay, back to polynomials. Now I see that we're kind of running out of the time, but anyways, I think we still have a time to shortly look at the polynomials. So finite attainment is about how is that we are describing the soul of an element. Soul, yes, like how is the inner life of an element, which is between the nodes. This inner life of an element will be described by using polynomials. That's what the shortly stated the finite attainment in structural analysis is about. All right, let me show you an example. So here is a spring element. So this is a structure that is a beam-like structure, but very special beam-like structure in a way that this structure has only like this longitudinal degrees of freedom. So there are two nodes, but the nodes cannot move any other way than back and forth in this x coordinate axis. X coordinate axis. So because there is only one way that this point here can move, it can move this way. I mean, if you think about that, what about if it goes reverse direction? That's still the same way, it's just a minus sign. And this can only move the one way. So there's a 1 degrees of freedom involved to this nodal location, 1 degrees of freedom involved to this nodal location. So what we're going to do in a finite attainment modeling is that we are approximating the behavior between these nodes by using polynomials. Now we have an element with the 2 degrees of freedom. So we're going to select the polynomial where there's a 2 unknowns, 2 polynomial coefficients that are unknowns. So we're going to get, don't worry, we're going to get back to this number of times. So we're going to use a polynomial, a 0 and a 1 multiplied by x. So if I would have one more node here in the middle, which 2 could move back and forth, then I can use a bit more complicated polynomial expansion, which will be a 2 multiplied by x power 2. And if one more, then I can keep on adding these components of these polynomials. Give me more nodes that I have within the one element, more complicated polynomials I can use as a general. There's of course some limitations in that. So now what we're going to do in the future is that we're going to replace these difficult unknowns, these polynomial coefficients which have no clear physical interpretation, by something that has a clear physical interpretation. What is a clear physical interpretation? Nodal displacement. This one and this one. And we're going to get something that is called safe functions. Safe functions are telling me exactly how is that I'm assuming particles between these 2 points to behave. That's what it is. Anyways, 9:45, so it's a time to close today's lecture. So that's about it. So yeah, so you may wonder about what about the carrier counseling today? Now what happened yesterday was I was kind of busy, but I'm sure you know because of what, cling is snow, of course. And I did not have a time to put together a presentation about the carrier counseling. But if you wanted to get the carrier counseling or additional lecture regarding the carrier counseling, this time more towards like how is an academia, I can offer that to you. Please let me know if that's what you would like to get, and I for sure can prepare a presentation for you, but not today. It's not going to be today. It can be, however, on next week Friday, not Friday, Monday. But let me know if you want, and if I don't hear from you, then I assume that you really don't care about that. Okay, so with that, I would like to close today's lecture, and if you would like to get this carrier counseling, email me. Okay. Um, I guess that's it. So we spent an hour and a half, so it's a time to close. And so thank you very much, and see you guys around next week, Monday at 8:15. 8:15. That's when we're gonna get started.